Okay, so welcome everyone that showed up. Um, so I thought, like I said, usually I like to give kind of a comprehensive list of things that we've done over the last few weeks so that you can be refreshed on what it is you actually need to know. So exam one covers uh, chapters 11 and 12. Okay, in the textbook. So the chapter 11 stuff is the basic vector, basic R3 stuff, basic vector computations. Yeah, I should say chapter 11. Um, so first thing is basic vector stuff. And what's included in that is how to find the component form of, say, a vector with initial point, terminal point. So this includes writing out, say, the formula for given initial point, terminal point, writing out how to find that vector. Being comfortable dealing with vector quantities. Basic vector stuff, writing out things like this. Being comfortable with basic vector computation. So this includes things like, two vectors, say u plus minus v, what it means to scale a vector by a constant. Geometrically, you can also write out what the interpretation of these things, and what they mean geometrically. That will help what these mean geometrically. You don't need to draw a picture necessarily, but you should at least understand, what you should be able to draw a picture of this, even though you're not going to be asked to do that specifically for the exam. Okay, so all that goes without saying, because really you can't do the rest of this stuff without, this familiarity, this stuff that we covered in like the first two lectures. Okay, dot product, obviously. So you have two vectors, A dotted with B. You should understand geometrically what it means. Right? So geometrically, this is our way of checking whether or not two vectors are perpendicular. So remember, A dot B is equal to 0 if and only if A is perp to B. All right. For the dot product, of course, there's all of the algebraic properties of dot product. You don't have to think about memorizing this too much. You should be able to work it out just from the definition of the dot product. If you need to, you should, of course, know this fact, right? Specifically, this is a special case of this relationship between the dot product of vectors and the angle between them. All right, so you should know this, that a vector A dotted with a vector B is the same as the length of A times the length of B times cosine of the angle between them. Right? Okay. You should, of course, know cross product, how to compute it. Okay. You should know geometrically what this means. So what was our primary reason for computing a cross product in this course? I'll let someone answer in chat. Someone's asking about how many quiz or exam drops. No exam drops. Quiz drop, there will be at least one. At least one. It depends on how many quizzes we have. Ultimately, if we have about 9-ish quizzes, I'll drop one. If we end up having like 11 quizzes, I might drop two. I don't know. So at least one quiz will be dropped. Okay. So what's the main reason we compute cross product in this course? This is to find a vector that's perpendicular to both u and v, right? So recall that u cross v is perp to both u and v. Right? So that's kind of the most important thing to remember about the cross product. Okay. Together, right, we can define kind of a triple product which computes the volume of a parallelepiped, right, determined by three vectors. So volume of parallelepiped determined by three vectors, say u, v, and w, is the absolute value of u dotted with v cross w. Of course, you can do this in any order, right? So you can do this triple product in any order. Another thing, right? So cross product is a lot of people. Someone said orthogonal equal normal equal perpendicular. Yes, all those are synonyms. So orthogonal, normal, perpendicular, it's all just perpendicular. The original reason why there might be another word to describe this notion is that perpendicular was always the thing that was used in 2D, right? So, of course, orthogonality in space is really no different, but because it's in space and there's an extra dimension, sometimes, and especially when you have higher dimensions, even more than 3, for whatever reason, this term orthogonal became kind of the standard way of referring to it. It's a synonym for perpendicular. So orthogonal, normal, perpendicular, however you say that, it's all the same. Okay. So of course, another interpretation of cross product is that u cross v, right, is the zero vector if and only if u is parallel to v. While that's neat to know, of course, this is something you shouldn't do to check if two vectors are parallel, because it takes too long. You can just, if you have two vectors, you can just tell whether or not they're parallel. That's included in this basic vector stuff, like definition of parallel. So definition of parallel vectors. Okay. All right. So this is some of this basic stuff. What else should you know from Chapter 11 stuff? So the equations for lines in space. So equations for lines in space. Okay. So both parametric and symmetric. So what geometric info is needed to write down the equation for a line in space? You need a vector L that is parallel to the line in question. So maybe here's my L, right, ABC, and you need a point that is on the line. We'll call that point x naught, y naught, z naught. Okay. So the parametric equations, maybe I'll write the parametric equations here. So parametric equations are, x is equal to x naught plus at, y is equal to y naught plus bt, and z is equal to z naught plus ct. Right? So these are the parametric equations. Okay. Of course, you could write this as a parametric curve if you prefer. So if you prefer to write this as a parametric curve, continuing on here. So alternatively, you could write this as a parametric curve for t in all the reals, since it's the entire line. X naught plus at, I plus y naught plus bt, j plus z naught plus ct, k. Okay, so this is perfectly fine too, using the fact that we know this is just a special case of a curve, right, in space. Okay, so this is also a parametric form. That's fine. So another form for writing out the equation of lines, symmetric equations. So symmetric equations, what do those look like? This is x minus x naught over a is equal to y minus y naught over b is equal to z minus z naught over c. Now remember, this is if A, B, and C are non-zero. If one of these or more of these, so if one or more of these is 0, you have to alter this, right? So look back at your notes to remember how to do that. Okay, these have to be altered slightly if one of A, B, and C is 0. Okay, so that's both types of equations, both types of ways of writing the equation of a line in space. So of course this means that any equation for a line, any line that shows up on the exam could be given to you in parametric form, or it could be given to you in symmetric form. Or if I ask you to find a line, say the line of intersection of two planes, then you should be able to write it in either form I ask. So maybe I'll say write down the symmetric equations for the line of intersection of two given planes. Okay, that's something that could be asked. So you should know how to give either form. Okay. All right. So next, the distance from point to line. How do I compute this? Well, I need a little bit of info here. Right? I need the point not on the line, and any point on the line will work. And this distance is the length of vector L that is parallel to the line cross P0 P1 over the length of L. So this is the distance, I'll write this, this is the distance from the point P1 to the line L, where big L is parallel to the line little l, or script L, and P1 is point not on L, and P0 is any point on L. Okay. All right. So that's how to compute that distance. Okay. Lawrence, first form I wrote up is parametric form. Yeah, this is just one version of the parametric form. This is writing it as a parametric curve, right? The original way that we wrote out parametric form was like this, but those two things are the same. Okay. All right, so that's distance from point to line. Okay. When I say you should know how the equations for lines, of course that means that if I give you enough info to write up the equation of a line, you should be able to do it, right? Whatever form it takes. So if I give you a point and a vector that's parallel to the line, so if I give you point on line, vector that's parallel to the line, then you can just write it down immediately knowing those equations. But what if I give you 2 points, right, and ask you to write down the equation for the line in space that passes through them? Then you would have to cook up the data that you need to use those equations. Okay. All right. Lastly, so equations of planes. So equations of planes, remember your general plane equation looks like this. Okay, that's what it looks like. An easy way to get this from point P0 on plane script P, and from N, the normal, to P. If N has components A, B, and C, and P0 has coordinates x0, y0, z0, then a particular form this takes is A x minus x0 plus B y minus y0 plus C z minus z0 is equal to 0. Okay, that's the equation for the plane with point P0 and N, the normal vector to it. Question in chat. Samuel says, will it cover 12.6? 12.6 is curvature, so yes, it will. Okay. Okay. So, what else about plane? So, in addition to knowing, say, how to cook up the equation of a plane given enough info, so say given 3 points, right, you should be able to write the equation for the plane and space that passes through those points. You also, if I give you the equation for the plane, should be able to tell me some points on the plane, and you should be able to tell me some stuff about it, right? You should certainly be able to tell me, whether or not two planes are parallel or intersect, things like that. Okay. Of course, distance. This is 7. Was this 7? Or I guess it doesn't really matter. This was 7, not 8. So distance from point to plane. All right, so this distance similar to before, except now you have n, a normal vector to the plane, this vector p naught p1. P sub 1 is the point not on the plane. P naught is any point on the plane. And this distance is given by the absolute value of n dotted with p naught p1 divided by the length of n. Okay. So this is actually easier to compute than the distance from point to line, typically, because this is a dot product rather than a cross product in the numerator here. Okay. So like I said, you can treat that list. That list is mostly exhaustive, right? There may be some little tiny thing not covered there, like one single thing that I said that's not covered. But that's pretty much everything that's needed. So it's more or less an exhaustive list of what you need to know. Of course, when I say that, I don't literally mean all you need to know is exactly what I wrote on the sheet, right? You should know all of the connecting stuff that allows you to do all of those things, right? Which is why I'm not expanding on it, because obviously if I could do all of that in a single hour, then what was the point of lecture, right? The last few weeks. So anyway. Anyway, formula sheet on the exam, definitely not. So no formula sheet. You got to remember all this. Do we need to know application of forces, Coulomb's law? No, you don't need to know anything about that stuff. Yeah, I know there are textbook word problems. Those textbook problems are ancient. That list has been passed around for probably 20 years. So not every single one of the problems is relevant now to the way that we do the exams. So yeah, those are interesting problems, but you don't need to know that for the exam. So if I didn't mention it in lecture, you don't need to know it for the exam. Okay. And I didn't do any of those examples. Okay. So chapter 12 stuff. The first thing, this is something that students often ask that is not directly something that we mentioned before, but it's basically how much prior. So this is kind of like a pre-question. Does that make sense? We'll say this is like initial question. How much previous calc, so 1 or 2, knowledge is needed in these computations? So, for us in these early chapters, technically, like, no Calc 2 knowledge is needed yet. The only Calc 2 knowledge that we'll need in the entire course, basically, is some stuff we do a little bit later. But Calc 1 is really what's needed. Now, what exactly is needed from Calc 1? So another way of framing this question is, what do you need to know, right, from previous calculus experience? What do you need to know in order to answer or in order to do these computations? So as you've probably seen by now, a few things. You need the derivative rules. right? So one, you need to know all derivative rules. Cannot stress this enough. So product rule, quotient rule, chain rule. You need every single one of these. Okay. Now, yes, technically, okay, you could do the quotient rule as a type of product rule, chain rule. That's fine, uh, but you're still really doing the quotient rule. So you need product rule, quotient rule, chain rule. Of course, you need to know the facts like derivative constant zero. You need to know the basic derivatives. So included in this and basic derivatives. Okay. Will we need to know hyperbolic cosine and sine? No, but I think from now on I'm actually going to do that. So you all don't need to know it for this, but maybe to enrich some examples later after this exam, I'll just go over them really quickly so that I can use those because they're really really nice functions. They're actually in some sense they're nicer than normal sine and cosine. Is the numerator of the equation absolute value? Yes, Yuma. This is absolute value. The reason that has to be the case, of course, is that in general, a dot product can be negative, but that wouldn't make sense because it's supposed to be a distance. So just conceptually, that thing needs to be positive for this to make sense. Will the exam be during class time and in person? Yes, definitely. So please show up to the exam. So it will be during class and definitely in person. I'll send out another announcement later, just reminding you all of how it goes and the process and all that. Your exam has 3 questions, like I mentioned in lecture. Each question has multiple parts. So one question has like 9 parts or something. Will we need to draw parametrized curves and say whether it's smooth or not? You won't need to draw anything on the exam. You should definitely know how to say whether or not the curve is smooth. Okay, so maybe drawing helps you with that, but you're not going to be specifically asked to draw anything. Okay, all right. So you need product rule, quotient rule, and chain rule. For integration, you need to know basic integrals. So you should know, integral e to the t, polynomials. If you know the basic integration rules, then polynomials once you know t to the n, right? You know that, you're good. 1 over t, of course, sine, cosine, etc. Right? Those are the basic integrals. You should know basic integral rules. Okay, and you got to know substitution. Not just for this exam, but also just in general. So going forward, you have to know how to do basic substitution integrals. As it turns out, this is basically all you need. Okay, so this is basically all you need, not just for this test, but also for the rest of the course. There's like 2 exceptions that I'll talk about when we get to them. Okay, so this is the initial questions, but you very much, like, Chapter 12 really hinges on your ability to do Calculus 1. Like, it's really just the Calculus 1 chapter. Okay, it's like, yeah, you're computing vector-valued things, but you're really just doing Calculus 1 in each slot, right? So, and keeping track of the algebra. That's it. No integration by parts is needed. Will we need to find tangential and normal components of acceleration? No. Okay. You should be able to find v and a. You should be able to find velocity and acceleration, but you don't need to find the tangential and normal components of acceleration. Okay. All right. So, more Chapter 12 stuff. Basics of vector-valued functions. Okay, so this is really our characterization of vector valued functions as, you know, a vector of functions, right? It's a vector of scalar valued functions. T is in some domain D. Okay. Gonna post this review. It will, Cameron. This video will automatically be uploaded to YouTube when I'm done. So, but it won't be public. I won't make it public, but you can access it from the link. Okay. So you can access it from the same link that you used. Okay. So, secondly, parametric curves plus basics. So when I say basics of vector valued functions, of course, I'm including, simple arithmetic that you might do involving them. That's not going to feature too heavily in the exam, but it's still something you should know. Parametric curves plus basics of parametric curves. It means if I ask you, right, is some point, is some point on this curve, you should be able to answer, right? So if I say like, is point minus 101 on this specified parametric curve, you should be able to come up with the answer to that, for example. Okay, and so the primary things, of course, to note here are length, or maybe before I talk about length, I should say definition of a smooth curve. Have to know this, and piecewise smooth. So intuitively, right, a smooth curve maybe looks something like that. A piecewise smooth curve looks something like that. These are the only types of curves you'll encounter. You might ask me, is there an example of a curve that's like continuous, but it's neither of those? And the answer is yes, but well, okay, I can draw it real quick. Well, I can draw kind of what it looks like. Yeah, so it looks something like this. If you're interested, it's called the Weierstrass function. This thing's continuous everywhere, so it's got no breaks, but it doesn't have a derivative actually anywhere. So it's actually somehow worse than being piecewise smooth, just having a cusp. It actually has infinitely many cusps everywhere. If you look at this piece, you say, oh, that piece looks kind of smooth. Let's zoom in. You zoom in, and what do you get? Oh, more of this. And then you say, okay, well, maybe this sub piece looks smooth, so let's zoom in. What does that look like? It looks like this. Okay. So, anyway, that's what that looks like. All right, but you don't have to worry about that for your exam. Okay. So, what else? Well, once you know what the definition of a smooth curve is, what's the definition of a smooth curve? So r prime exists, and what is very important is that r prime of t is never equal to the 0 vector for all interior points of the domain. An easier way to check this sometimes is to instead compute the length and check that that's not equal to 0. Okay, sometimes that can be a little bit more straightforward than trying to see whether or not this thing can ever be the 0 vector, because you're checking like 3 components here. Here you're checking a single number, right? If you like. Do you need to find limits, domain ranges? No, Joy, you don't need to worry about that. So no, you're not going to be asked to compute a limit or anything like that. You're not going to be asked about domains or anything either. Okay, but you do need to know about the definition of smooth curve. Okay, you need to be able to find length of curve. All right, so what's length of curve? Length of curve is if you have a curve C, it has parameterization r of t, it is smooth. That's what you need. And t, it belongs to the closed interval a to b. So maybe this is a closed curve, or maybe it's just a piece of a curve. In either case, the length is the integral from a to b of the length of r prime of t dt. So this is the length of the full curve. You also need to, as I wrote on the board yesterday, you need to know about arc length, which was this function s of t that defines the integral from a to t of the length of r prime of u du. Okay. Note, of course, that s of b is just equal to the length, right? So what is arc length computing? As I wrote on the board yesterday, if here is r of a and here is r of b, the entire length, of course, is, well, the entire length of that curve. The arc length up to some t is just the length of this portion of the curve. All right, so this piece is s of t. All right. So that's what that's computing. All right. And of course, as I mentioned yesterday in lecture, whenever you have a quantity written like this, defined, where you have a variable showing up in the limit of integration, what this should tell you is that you want to use fundamental theorem of calculus. So we use fundamental theorem of calculus here to compute the derivative of this thing. ds dt is then the length of r prime of t. Fundamental theorem of calculus is the thing that tells us that, well, all I do to compute the derivative of this thing with respect to this variable showing up in this upper limit is just plug that variable into the integrand. Right, that's it. Okay, should we be able to identify equations as certain shapes and how it changes? Yeah, that is something like conceptually you should be able to do. Mechanically, you could get away with not having too much visual understanding for this exam, because the exam this exam is not too conceptual in terms of those things. So you don't have to worry too much if your visualization skills are, not up to speed yet, because it's not. This exam doesn't really rely too much on it. Okay. All right. The visualization stuff really is not going to be required kind of until like chapter 14. Okay, so you don't have to worry about it too much right now. Okay. Of course, tangents and normal vectors to curves. So tangents, normals, and curvature. All right, so we have a curve C. We'll say it's smooth, right? And we'll say it's smooth, and also it is nice enough that all these things are defined, right, everywhere. So r of t, of course, the usual notation, x of ti, y of tj, plus z of tk. Okay, t is in some domain D. Okay, this describes the curve. The unit tangent vector at the point r of t is given by what? This is r prime of t over the length of r prime of t. The unit normal vector is then computed from the unit tangent vector. So this is, of course, a function of t. This thing, even though you're taking a length, it's usually a function of t. In some special cases, it's a constant, right? So a circle is a good example. The usual parameterization of circle, that thing's a constant. But in general, it's not. Okay, it's a scalar valued function of t, typically. All right, and so unit normal is t prime of t divided by the length of t prime of t. Okay. And of course, once you've computed those quantities, computing the curvature kappa of t at the point r of t is simply the length of t prime of t divided by the length of r prime of t. Okay, so that's how these things are related. So in general, in these problems, you start out with r, you have to compute r prime, length of r prime, that gives you t. Then you compute t prime, length of t prime, that gives you n. In computing both of these, you have computed enough info to write out the curvature kappa. Okay. So this is what is needed to do this. This finishes 12.5 and 12.6. This is what's needed here. So then the question is, like, notice that there's not a whole lot of formulas that you have to like remember or anything. So in terms of memorization, this exam is very, very light on memorization, right? I'm sure whatever, if you're in a chemistry class or something, you're having to memorize like 50 times the amount of stuff for your exam than you are for this class. There's very little stuff to actually memorize here. And so that means that the vast majority of the points you get on the exam is going to come down to doing the calculus and algebra. So it's correctly computing derivatives, correctly simplifying these things to make your life easy. The thing I will tell you that will save you the most amount of time possible is always simplify t as much as possible. Okay? This is not a thing like, oh, if you don't simplify, you don't get the credit. That has nothing to do with it. This is, if you do not simplify the tangent vector, this is purely for your own good, then your computation of n is going to be awful, right? And the chance that you make it through without making some algebraic mistake is almost zero if the tangent vector is not properly simplified. Okay, so always make sure that t is as simple as possible, okay, before going on. You will, on the exam, you will be given curves for which this is not too bad, right? So if you wind up with something that you feel is really, really obnoxiously bad, it means you've done something wrong, okay? Now, of course, maybe you just have ridiculous standards for what bad means, but that's not usually the case. It's usually, if you look at the thing and you're like, I feel like this is a lot nastier than it should be, it probably is. Okay. Will you need projection of vectors? I could have put that on the exam, but I'll go ahead and tell you that I didn't. So, I could have put that on. I was looking for one more, and I chose something else instead. So maybe next time, next semester, I'll do that. But yeah, no projection of vectors, mostly because, like I said, I forgot about it. What would you say is good versus bad in terms of what we should see? Well, when you compute these things, so I should say, you don't have to worry about simplifying n too much. And the reason for that, and so in fact, if you've computed n, you have t prime, you've computed it, and length of t prime, and maybe it is kind of nasty. That's okay. So it is okay if n is nasty. Why? Why is it okay if n is nasty but not t? Once you write down n, you're not doing any more computations with it. So you don't care if n is nasty, you're done. You write it out and you're done. In fact, if it has a really long expression, once you've written out t prime and once you've written out length of t prime, you can just say, well, n is this thing. You don't have to spend all the time writing out both of those things again. Okay, you can just write the formula for n there instead. But for t, you have to compute with t, right? That's how you find n, is computing with t. So that's why t needs to be as simple as possible. But n, once you write out what n is, it's it. You're not doing anything else with it. So you don't have to worry too much about simplifying with n. In terms of what is considered nice, are there practice exams somewhere? Yuma, yes, there are practice exams in the UMD test bank. Okay, so if you use your search engine of choice and look for UMD test bank, okay, you will find it. There's a database of exams going back like 20 plus years, okay, to like the late 90s. For this course, all of those will be perfectly fine. Most of those exams posted are going to be final exams. Not a big deal. Just pay attention to the chapter 11 and 12 material. Okay. So don't focus on the later stuff. You'll clearly know what's the later stuff because you won't understand it, right? So, can we calculate cross products using the formula? I mean, whatever formula you use to compute it, you should write it out. So don't do it entirely mentally. You should write it out. If you use the method of, writing out the alternating sum of triple products, that's fine. Just write that out. Don't just do it in one step mentally. Okay. All right. Yeah, I mean, like I said, the main thing I was going to say is almost all of the points on these problems, right? And doing calculus on curves for this exam is literally like 60% of the exam. So 60% of the points on your exam is going to come from doing calculus on curves. So you should practice your derivatives. Make sure you know all your derivative rules and practice your algebra involved with those things. Okay, that's the most important bit. Okay. So, any other questions about the exam? Let's see, let me see if I answered. I think I answered everything. If we saw a number like cosine 5 pi over 6, should we know this exact number? Yes, you should know that. You should know that. Use reference angles, right? So you should know unit circle and reference angles. Now, I don't expect you don't need to know like how to use cosine and sine identities to get, cosine of pi over 12 or whatever. You don't have to worry. Don't worry about that. So you don't have to worry about, complicated. But cosine 5 pi over 6 is okay. That's fine. It will be 50 minutes, Tal. So it will be 50 minutes. Are the binormal vectors on the exam? Well, technically, I mean, binormal is just t cross n, right? So if I asked you to compute, say, the binormal vector, or I could even phrase it like this. I could say compute the normal vector to the osculating plane, right, at a curve at a point, right? That's computing the binormal. So no, you should know binormal is just t cross n, so that's all you need to know about it. Do you get partial credit for work, Yuma? No, it's graded in binary. You either get 1 or 0 for every single question. That's it. There's 3 questions, so the max score is 3, the min score is 0, and good luck to everybody. But no, the answer is yes. You definitely get partial credit for work. It would be there would be some lonely majors if you didn't get partial credit for this stuff. So you definitely get partial credit for work. So how much partial credit you get, of course, depends on how egregious your mistakes were, and that's why really be careful with these initial computations you do. Right. So for instance, I'm glad you mentioned this because as you can see from this problem, if I gave you a problem that was curve, here's parameterization, and I asked you to compute tangent normal curvature, okay, right? What happens if you screw up this derivative? Right? What happens if you screw up r prime? Well, everything else is wrong after that, right? So literally, if you go to take that first derivative and you make a mistake, everything else that follows is totally wrong. Okay. Now, if that error was something slight, if it was just a difference in constant or something like that, that's not a big deal at all, and it's very easy for a TA to track through to try to give you points on the subsequent parts based on how you computed them. So The TA is going to try to do that anyway, okay, even if your mistake was larger. The problem is that if the mistake is particularly egregious, sometimes the work afterwards becomes so, nonsensical that it's hard for partial credit to be awarded, and that's why in these problems, be very, very careful with your algebra, especially early in a problem, because that's how to maximize points. Also, be very clear with what you're writing out. So just immediately writing these formulas out is good because it's, one, showing the TA that you know at least these formulas, you know what you're trying to compute, and then it also helps you keep track of what it is you're doing. Our exam's cumulative after this one. So actually the way Calc 3 goes is the material is kind of in chunks that are mostly don't have anything to do with each other. So so there's the chapters 11 and 12 stuff. That's one chunk. Chapter 13, that's going to be your next exam chunk. That is kind of totally separate, so you're almost resetting after this exam. And then the chapter 14 stuff, you're also almost resetting. It's totally different. It doesn't really rely on the other stuff. And so for your 3 in-class exams, the answer is no. They're kind of independent. But for chapter 15, the last stuff we do, absolutely everything is used. Okay, so that's where everything comes together. Chapter 15 stuff it typically constitutes like 20% of the final exam at most. So so I would say that there's a 20% chunk of the final exam that is cumulative material, and of course the final exam itself is cumulative in the sense that it has all the other chapters in it. But the answer is it's not really. These exams aren't really cumulative. Your chapter 13 exam will not rely on any chapter 11 or 12 stuff really, other than some of the really, really basic, like just how to do vector computation stuff, dot products and stuff. Tangential and normal components of acceleration on the exam, no. Yeah, I already said no. That's not on there. And so that's more or less the overview. Any other questions? Oh, right-hand rule, I see. So the right-hand rule for crossing vectors. So imagine that I have a vector A here and another vector B. Doesn't look that straight. And I'm wanting to compute A cross B, or even if I don't compute A cross B, I'm just wanting to know what direction A cross B should be pointing. What I do is I take my right hand, put knife edge of right hand along the first vector, so A in this case, okay, or parallel to A. And then I let the fingers in my right hand curl towards the second vector. So since B is there, it curls towards B in that way. And once I'm in this position, the direction my thumb points, if I have my thumb held like this, is up. That is the direction of A cross B, is pointing straight up out of the page in this case. So if I were crossing 2 vectors and it looked like this, using my right hand rule doing the same thing, I need to curl my fingers towards B. So in order to do that, I would have to flip my hand and it would point down. Okay. So in that case, my vector would point down. So that's how the right hand rule goes. Let's see. How to compute visualization, or sorry, how to improve visualization. Practice. It's just practice. Seeing a bunch of examples and practicing. And I will, when we get to more of that stuff, I will give you all plenty of examples of stuff you can look at in terms of visualization. Joy, do we have to calculate areas of parallelograms and stuff? So that is actually included in the volume of parallelepiped stuff. That's just like the lower dimensional version of it, basically. Actually, if you compute like the length of V cross W, this is the area of the parallelogram determined by V and W. Okay. Like I said, this is kind of like a lower dimensional version of the volume of a parallelepiped stuff. Anything else? I think I answered all of the chat questions. Do I recommend rereading the textbook? I mean, the textbook is great for I mean, that's like the course is following the outline of the textbook pretty closely. So, like if you go through the textbook, you'll be following the lecture schedule like almost identically as far as the sections go. So it's roughly one section per day. Some sections are larger. Only a few sections get skipped. So in chapter 13, there will be a section I skip. But apart from that, there's very few. There's only like a couple instances of when I actually compute. Um, where I compute something, or where I do like, or where I basically skip in the lecture schedule. I skip lectures. So we did it a couple times for early chapter 12 stuff. I didn't go through all of that stuff. 13.4 gets skipped in chapter 13. There's like one section of chapter 14 that gets skipped. Other than that, everything is done. So from 11 to 15. If we had a question on problem like from the book, is it okay to contact you or go to TA first? Either. So you can email me or TA and ask a question. Like if you have a specific question about something from the textbook, then you can definitely contact either of us. Can I go through an example parallelogram problem, like computing the area of parallelogram? Well, that's a cross product problem. So why don't instead so this is just computing a cross product in a length. So maybe let's do something. This is a question off an exam from last. I think this is an exam I gave. This is the exam I gave last semester. Let me see. Let me go through. Let me see here. I'll find it somewhere. I'm gonna yeah, so let's do as soon as this okay, so let C be the curve. R of t is, say, cosine t I plus square root of 2 sine t j plus cosine t k for all t in R. And let's write down the equation for the osculating plane to C at the point R of 0. Okay. All right. So, the osculating plane is the plane determined by t of 0 and n is 0. And so really we're looking for the binormal vector at 0. That's going to be our normal vector. The point in question is going to be R of 0. That's all we need to write out the equation of a plane. Okay. And so I have to compute tangent normal vectors to do this. So let's do that real quickly. So what's R prime of t? This is minus sine ti plus root 2 cosine t j minus sine t k. That's r prime. What's the length of r prime? So length of r prime is square root of sine squared t plus 2 cosine squared t plus sine squared t. So this is root 2. Okay, and so our tangent vector t of t is r prime of t divided by this length. So this is 1 over root 2, sorry, minus 1 over root 2 sine t. In the first slot, in the second slot, this is cosine t. And in the third slot, this is minus 1 over root 2 sine t. So that's t. Now to compute the normal, we compute t prime, sorry. So t prime of t is minus 1 over root 2 cosine t minus sine t minus 1 over root 2 cosine t. Okay, let's compute the length. The length of t prime t is going to be square root of, this is going to be 1/2 cosine squared t plus sine squared t plus 1/2 cosine squared t. So this is 1. Okay. And so the normal vector is actually just t prime. So the normal vector is just minus 1 over root 2 cosine t minus sine t minus 1 over root 2 cosine t. Okay. Now I have everything I need in order to compute all this stuff. So first of all, let's write out my 3 vectors. So so first of all, what is t of 0? So t of 0 is the vector 0, 1, 0. And n of 0 is the vector minus 1 over root 2, 0, minus 1 over root 2. Okay, so then my binormal vector is just the cross product of those two things. Okay, so if I write this out as determinant, again, you don't have to use this way of doing it. This is just kind of like the long way of doing it. You can do this however you want to, just show all your work. This is minus 1 over root 2, 0, minus 1 over root 2. So what is this if we do this component by component? So this is something times I. What is that something? 1 times minus 1 over root 2. Yeah, so this is minus 1 over root 2 minus 0. Minus something times j. Well, what is that? 0 minus 0. Okay, plus something times k, where this something is 0 minus 1 over root 2. Okay. Oh, I'm off the screen. There we go. All right, and so this vector is minus 1 over root 2 I plus 0 j plus 1 over root 2 k. So there's my binormal vector at 0. This is normal to that osculating plane. But the point on the osculating plane is the point on the curve specified, which is r of 0. My parameterization is here. So this is 1, 0, 1. Right? So here's point. Here is cross product of vectors giving me binormal vector, which is normal. So the equation of osculating plane is, so here's my n, here's my point. So this is minus 1 over root 2 times x minus 1 plus 0 times y minus 0, right, plus 1 over root 2 times z minus 1 is equal to 0. Now you could simplify that a little bit, but there's no reason to. That's perfectly fine. So there's my equation for the osculating plane. Now you might say, wait, you asked me to do, or I asked you to do a parallelogram problem. How does this relate? Well, to compute the area of this parallelogram, for instance, I just take the length of a cross product of two vectors. So imagine that the two vectors in question were these two, 0, 1, 0, and minus 1 over root 2, 0, minus 1 over root 2. After I found that cross product, I would just take the length of this thing, right? And that would give me the area of the parallelogram. Okay, so just wanted to do an example of one that kind of involved everything here. So anyway. Okay. So you have to be comfortable doing all of this algebra. So in lecture, I did an example that was very good for keeping track of the algebra. I did the logarithmic spiral. So in lecture, I did this example. E to the t cosine t I plus e to the t sine t j. This is a good example. Okay. If you know how to do this kind of example, then you'll be fine for the stuff on the exam, because dealing with this algebra is the worst that you're going to have to do. Okay, so any other algebra you would deal with as a result of this is going to be better than this, or it will be no worse than the algebra that results from that. Okay? All right, so anyway, that's your exam. Okay. So I will see you all tomorrow in class. Good luck on the exam. I'll wish you all good luck again later. I'll send out another kind of reminder announcement for how things are going to go tomorrow, and then you show up and take the exam, and then you'll be done, by 2:50, and you'll have it in the past, and then I'll see you in class on Monday. So anyway, exam tomorrow, 2 o'clock, in class. Definitely be there. All right. So I will see you all then.